Hello, everyone. Welcome to our system design session. So, thank you for joining us. Just 2 minutes while people joining, and we will start our meetup. While people joining, if there is someone who joined us first time, please send some smiles or something. So no one first time. Okay, we have one. Okay, just one. It's nice. So we have a new host today who is helping me with the event. For a learning purpose, I will anyway to introduce women coding community. So yes, it won't take a lot of time, folks. Just a couple of minutes, and then we will go straight to our session today. So I'm sharing my screen, and we'll start. Do you see presentation? Okay. So women coding community, building a safe environment for women to thrive in tech. Women coding community mission is empowering women to be at the forefront of technologies and innovation. Women coding community vision is empowering women in their tech career through education, mentorship, community building, and career service. We provide workshops, events, connect members with industry mentors, foster a supportive community through meetups and conference, and raise awareness for more inclusive industry practice. Code of conduct. At Women Coding Community, we are committed to a vibrant, supportive community where women can network, share experience, and foster professional relationship, regardless of the age, gender, visible or invisible disability, ethnicity, gender expression, level of experience, education, social economic status, nationality, personal appearance, race, religious, sexual orientation, and or prefer programming languages. So our projects, we have mentorship program with different length. It could be 12 months or it could be 3 months. We have book club, writing club, speaking club, career club, coding club, civic clinic. All of them has they Slack channel, which is you can join and enjoy conversation in this Slack channel. A part of it, we have different study groups and also not study groups and some programs which is running for free 4 months. So, for example, lead code study groups. We have machine learning bootcamp, which will run for 12 weeks. Lead code study groups, we have channel, but also we have lead code bootcamp, which is running for 12 months. Not 12 months, 12 weeks. Apart of it, we have some study groups like system design track, cloud track. This is community mainly focused on AWS certification. There is a lot of talks about who obtain certificate. There is a very supportive community. So if you are targeting to obtain any certification, so you can join this track as well. A part of it, we have mock interviews channel where we're trying currently to make it more active by posting real interview questions. to help you. For example, if you, it's absolutely anonymous, you don't need to share the company's name or something, just an interview question, which just will help the other people just to know what usually you can expect during the interview. So you also can join over the Slack. So we always need volunteers, as a mentors, as someone who is helping to us to promote or with some ideas to run this or that track, with meetup ideas or something. So benefits, quite often I see there is first you will learn in safe space, because the community is huge. Even though it was founded 1 year ago, but it is huge already. There is a lot of opportunity just to learn some skills in the safe environment, like leadership skills, or teaching, or mentoring, or answer some questions, or helping to grow this community for them. So, and it is very safe. So basically, no one is going to judge you. Just go, try, and make work better. So we have a lot of benefits. Quite often there is some spare tickets free, which is we're sharing through the community. Yeah. So basically, I believe that's it. And yeah, I think I'm finished. We're here. And now I will give my virtual microphone to Shailaja.
Hey, hi. I hope everyone doing great.
I will start recording. Yeah, 1 second. I'm starting recording, folks. Just now. Okay.
Okay. So till now, in the system design, we were talking about distributing the data across systems for horizontal scaling. Now we will deep dive into how we distribute the data into multiple machines on in a distributed system when we are doing the horizontal scaling. So in the last session, we have discussed replication, leader, and followers. So even for that, this concept is important for how we are distributing the data between leaders and followers as well. So let's assume we are having a horizontal scalable system, and we are having data across multiple machines. Now, when you're having data, you want to distribute the data such a way that you can have parallel requests at the same time going on, so we can achieve the higher throughput. And we also wanted to organize the data such a way that the data closer to the users of the access, so that the latency for them is lesser. So due to that, there are different strategies for data distribution. Please note that there is nothing like one is right, one other is wrong. We can based on the use case, we can use a different strategy, or we can use a combination of the strategies as well. I will give one example later on how we use a combination of the strategies. So the first one we are going to discuss in the data distribution strategies, the range partitioning. Let's assume you are having the data. So when for all the techniques we are discussing, one concept you need to remember: the partitioning is based on the column that we consider as a partitioning index. For example, if you are having a accounting table, let's assume your banking table, or whether you are having daily transactions of money deductions or money deposits, etc. In that case, the column for the data partitioning can be the date when a transaction happened. That is a column on which we do partition the data, because that is the column we use to access the data more frequently. There could be other columns where we might be accessing the data. For example, it could be another column based on the credits or debits, just to see the aggregated total credit amount, aggregated total debit amount, or another column like user ID. But those are all secondary use cases. That means the most frequently accessed data is the primary index. That is the one which is more important for distributing the data, because data access using the primary index is usually faster. For example, if you're having different table where you're having salaries table, let's assume in this case the column user employee ID. This can be the primary index, and this can be used for the column as a partitioning index. So based on different use cases, you can choose what is the user who is creating the table, who is the admin of the table, can be can choose the what is the primary index based on their use cases. Yes, there can be multiple columns as well. I will come to that later on. What are the different kinds of indexes that we will discuss after discussing the partitioning techniques. So for now, just assume that all the techniques we are doing are applied on the partitioning index, that is the column or set of columns on which we are distributing the data. Well, we'll come back to this later. Just for now, keep an assumption that all the distribution of the data is on the partitioning index. Now, so on the range-based partitioning technique, the first one we are discussing, let's assume you're having a accounting date, that is a partitioning column for your partitioning index for your table. Let's assume there are days like from January 1st to all the way from December 31st, let's assume. Then in that case, you can divide your data into the ranges. Let's assume all January data going into one section, all February data going into another partition. So the one thing you need to remember, the partition is also called as the shard. It's the same, both are the same. The shard, a partition means a piece chunk of the data that is going to a particular machine or a particular virtual machine. It could be a virtual disk. So in that case, you are distributing the data based on your partitioning technique. So in this case, in the range partitioning, you are sending a range of data to a particular partition. Let's assume this is the partition 1, partition 2, or you can always also call it a shard, partition 3, partition 4. Let's assume you're having 12 partitioning, let's assume. Yeah, for the more practical use case, you can say 31 partitions. Let's assume all day first data, month numbered 1 data, first date of the month is going to the one partitioning. Second day of the month, that goes to second partitioning, so on. That means January 1st, Feb 1st, March 1st, so on. All the first data is going to one partitioning. Then January 2nd, Feb 2nd, so on, going to another partitioning. Jan 3rd, Feb 3rd, so on, going to another partitioning, so on until the 31st of the every month here. Now, if you see, the main advantage of this approach is very simple. You're just taking a range of the data and distributing it. It's very simple approach. Second main advantage is, because you are doing the range one, you can do a range queries. For example, if you want to get all the data which is going to particular date, let's say the date span, for example, all the data from January 5th, all the accounting transactions happen between January 5th to February 5th, let's assume. In this case, you run range queries. All the data which are consecutive in the dates are going to be in adjacent partitionings. Let's assume from here, you're getting all January 5th data from the 5th partitioning, 6th data from the 6th partitioning, so on until February 5th. And you take all the data and then you merge the data. To be more simple use case, let's assume in one partitioning, in the one database value, let's assume you are having a values of January 1st, a timestamp T1, T2, so on. Then when you are reading the data, you just run it, you first look at the first record in the database, then you keep reading as long as the data is within the range. So this helps us do the range queries, which are faster. And this kind of use cases are very common. For example, if I am creating a ledger for at the end of the month or at the end of the year-end ledger, then I just take the range of the data, last 1 month's data, last 1 year's data. So this kind of range queries would be very efficient and faster. This is main advantage of the range partitioning. The main disadvantage of this partitioning is the data can be skewed. For example, if you see the 31st of the month data, usually because not all months are having the 31st, so this partitioning is more likely to having lesser data. Whereas data on the January 1st is going to be higher, mainly because it's a month beginning. Bankings do have a special transactions on the month beginning and month end of the month. So something like creating the ledgers, sub-ledgers, etc. So those transactions probably having higher data. So the problem is there is a skew. So that means like one partitioning is having a higher data in the bar chart, another partition is having a lesser data. What is the problem with the data skew? When you are reading the data for this partitioning, your query has to deal with higher amount of the data. Whereas the query involving the partitioning of this one has to deal with the lesser amount of the data. So when the one query, single query is having lots of data to deal with, it becomes quite slower because it has to read through all entire disk, then filter the data based on your where classes, etc. And then it has to return the data. So that's going to be the higher disk reads. The other one is when you're filtering, you're bringing lots of data into the memory, then you're applying the filters on top of that. But depending on the use case, some filters can be on the disk, some filters can be applied in the memory. So that's also requires lots of memory pressure and the CPU to do the sorting, filtering, etc. So that's the reason we try to avoid data skews or reduce. It's not possible to avoid all the time. We try to reduce the data skews as much possible as we can do. So this first technique of range partitioning it's very useful for some of the use cases, very simple to implement. But the problem is data skew is a problem. And the more important thing you need to remember about this range partitioning is range query is going to be very efficient. And this is very important for some of the use cases, even when you are doing system design interior or even real system designs. If you think your use cases are having range queries most of the time, then you need to probably consider range partitioning.
Can we take some questions? So first question, can we use multiple columns for partitioning?
That's I did answer. So the when I say partitioning index, just assume that it's as abstracted one index per now. Partitioning index can be multiple indexes, and depending on different systems, indexes can be organized differently. We will come back to that later in this one because that requires a bit of explanation further. For example, once we are done with all this one, we come with a composite index. That's where we explain how these indexes can be multiple columns as well. Yes, just for now, abstract, assume that one single column here, because we need to make it more simple for people to understand for now. I don't want people to keep thinking too many things at the same time. Just for now, assume that just one index. Once we understand these things, then we will jump into what is a primary index, what is a computed index, what it can be. Primary index can involve different columns or not. Again, different systems are having different way of creating the primary index. So just keep it aside for a while.
The second question, can there be only one partition index at the time?
Yes. So partitioning index, there can be, again, so this we will be covered later, but I will quickly answer. Partitioning index X is the index on which you are physically distributing the data. So there can be only one way of physically distributing the data. There is only one partitioning index. Whereas there can be other kind of indexes. So for example, secondary indexes. You can create as many secondary indexes as you want. There is nothing restricting that. But the partitioning index, the partitioning index is on which you are you're moving the data across the systems. Because you're moving across the system, there can only be one way of doing that. So there is only one partitioning index.
Okay. Can I just briefly, just to sum up, maybe it will be more clear if someone also. So basically, what Shailaja started, she started from partitioning data. We learned that we can replicate data, and we can now we are learning that we can partition it. When we're speaking about replication, we are speaking. So, for example, we have our service, which is new one, and there is data which is we can place on one machine. But sometimes when we are growing in our service is not able to hold all the data, one of the reason we will go with partitioning. This is one of the reason. Another one reason, which is Shailaja is currently trying to explain, it's about how we are reading. It's also speed up writes as well, partitioning, because we are splitting data. So assume we have like a font dictionary with from A to Z, and instead of holding all these numbers from A to Z on the one machine, we are splitting in 5. So basically, we can speed up the read process from them. Yeah. So basically, this is the idea of partitioning. Sorry, Shailaja. Yeah.
There are two things I need to correct that. Right now, partitioning and application is two different things here.
Yes.
We are right now only talking about the primary copy. The replica copies, for example, there can be different strategies for the replication. For example, in this
No, Shailaja, don't go to replication. Stay.
That's exactly.
Yes.
I would like to take questions at the end of the session. That's the reason. So don't get confused. I know too many things at the same time. That is one thing. Second thing, sorry, you mentioned something. I forgot. Yeah, there was another point I forgot when you were talking. Okay. So right now.
Can I just ask one quick question? So you're talking
Yeah.
about partitioning, right? Is this partitioning because you're saying we partition the data across multiple nodes, but can partitioning also happen on the same node? Or
Yes, there can be multiple partitioning sitting on the same machine. If you're just looking at the one physical machine, there can be multiple partitioning sitting on the one machine. So, for example, if we are having a very huge capacity of the machines, and in one machine there is a huge capacity, and they still wanted to isolate the data based on some strategy, then you can have multiple partitions on the same machine. Is it going to be on the same machine or multiple machines? That's abstracted from the partitioning strategy. It can be any strategy. How are you going to decide on which machine it is going to? That's where when we are accessing the data, we usually apply an algorithm how we are going to choose, or we decide for which machine this is going to, and from which machine am I going to read from. For example, in case of the range partitioning, it could be simple formula. Let's assume I have a accounting date coming in. So I'm having a accounting date coming in. On the date, let's assume I will just apply date percentile 31st. So this gives me, if it is first, that means I will go to the first partitioning. If the value is second, that means I go to the second partitioning, and so on. So the same technique while writing, the same algorithm we use, the same algorithm we use while reading as well. So there are some algorithms which requires this mapping to be written somewhere. There are algorithms which doesn't require this mapping to be written somewhere. In case of the range partitioning, a typical simple range partitioning doesn't need to have any mapping written saying that first has to go to this partition, so on. It can be simply a simple formula, something like this one. But a complex range partitioning probably needs to return the mapping somewhere. So we'll come to that in the custom mapping, which is coming next. I will show you that.
What I'm asking is, at the end of the day, no matter which partitioning strategy we use, the idea is not that it's not like only one partition will be present on a machine. A machine can host multiple partitions, right? And it should actually as well.
Yeah. So, for example, if this one is coming as a first, You can say that you can have a mapping somewhere saying that all the first 5 will go to the machine 1, and the machine 1 disk 1, machine 1 disk 2, so on. So you can have machine 1 disk 3, so on. This kind of mapping you can do. Or else you can just give each of the partitioning a virtual ID and simply say that this one is going to virtual ID 1, partitioning data 2 is going to virtual ID 2, so on. So the disk ID, the disk where it is going to, the database, the disk where it is going to is the actual physical one, but the one we are calculating could be the one virtual node ID, the virtual node ID. The virtual node ID probably mapping to a different disk on the same machine, or could be mapping to a different machine.
Okay, that makes sense. Thank you.
It's Moina, it's also very depend because when we're speaking about the strategy, partitioning strategy, it's very important to understand how you're going to partition this data. So, for example, if you have a service which is work globally, so for example, and you store data per Japan, for example, per US, you don't really need to store this data from Japan on the US machine. For fallback,
And actually, can you please give me some time? We are going to region-based partitioning next, so too many things
okay,
mixing
sure.
together.
You're
This
going
will disturb my flow. So I have a plan. Let me go through my plan now.
Sure.
Okay. So second one is the directory or custom partitioning. This is like having a this is the one I mentioned. So you can have your own custom mapping. It doesn't need to follow any particular algorithm. But there are advantages, disadvantages. I did work on real systems which they use custom partitioning as well, though it has its own disadvantages, but it has advantages as well. So in this case, what happens? You do maintain a configuration that says that when you are having a primary partitioning index, on partition index, you apply some algorithm. It could be some hash value, it could be just the direct index value, whatever. And you say that these set of values, primary in partition index X, Y, Z, go into machine node ID 1. ABC go into node 2, so on. So this here in this case, there is no particular algorithm directly applied on the partitioning index. Instead, you maintain a mapping. Or you can simply say from all the values from 1 to 10 going to node 3, whereas the all values from 10 to 60 going to node 4. So it doesn't need to be really exactly a algorithm we are following. In this case, the main advantage of this approach is you can customize the configuration as per your requirement. It can be any way you want. Doesn't need to really particular formula, algorithm, or particular way of doing that. The problem with this approach is you need to have this configuration stored. Usually a centralized node, you can say that's something like a configuration server. It could be Zookeeper, where you're writing your configuration. And after that, you will take the value. For example, when there is an incoming request, you check for which partitioning node it is belonging to. In the lookup table, you can say that lookup table, if it is this one, we go to the node 2. And in this case, the problem is there is one single point of failure. If the centralized node is failing, then you won't be able to access the data. That's the reason there is the main disadvantage of this approach is the centralized single point of failure. The other option approach is whenever you're changing your configuration for some reason, for example, adding more nodes, N5, N6, so on, when you're adding more nodes, you are going to change your configuration. That means whenever you add nodes, whenever you remove nodes, your configuration keeps changing, and you need to deploy a new configuration to the servers. And most of the time, this centralized config usually we maintain a multiple copies of this one, because if one machine is going down, we don't want this configuration mapping to be lost. So whenever you maintain the copies of this configuration, you need to update the configuration and keep them sync in all other places as well. For example, XYZ change it to N10, then we need to update this configuration to XYZ to N10 in other places as well. So that's the reason. The main advantage of this directly a custom partitioning is you can customize the partitioning, the algorithm the way you want. It can be anything. But you need to maintain a mapping of how you are doing that. You need to write it down somewhere how you're doing that, and you need to maintain multiple copies of that. And whenever there are changes, you need to sync all the configurations to the same one. Yeah, this is the second one, custom partitioning. The third one is the region-based partitioning, the one that we were talking about. So in case of region-based partitioning, we usually partition based on the location, it could be country, it could be city, or it could be any, there is nothing like we need to be at this city level or the country level. It could be anything. For example, even within the city, you can have a small region, sub-regions distributed. For example, if you take a request coming from the US, California, probably you're sending the request to one data center. If the request is coming from within the US from the Texas, you're sending the request to another one. Or if your request is coming from UK, you're sending the request to another data center. So that's how the region-based partitioning works. So main advantage of this approach is, as we already discussed about this one last time during the replication, we are having the data closer to the location where most of the users access. For example, if all the US data is within the US, any announcement that Trump makes, then all US people can see them immediately. The UK people will probably see the slightly higher latency when UK people are reading from the US system. But all the UK related data will have the low latency because we are seeing that we are reading the data from within the same region. That's the reason. So here, if you see low latency for region within region requests. And another advantage is, for example, in the US, if we are having let's say, some disaster, it could be storm, it could be anything. If one data center goes down, it doesn't impact other data centers. It could be UK or other regions within the US. They are still active, up and running. So you're isolating all the disasters impact to one particular region. Still, we won't lose data in those situations. We can record the data from the replicas, but the other data centers, where other partitions in other locations are located, they don't see any impact because of that. And the other advantage, and nowadays is really very important because each country is coming with their own regulations. For example, Europe is having its own GDPR, China is having its own regulations. So when you are keeping a country's data within the country, it's more easy to follow the country's regulations. Most of the countries nowadays asking you cannot keep our citizens' data in other countries. In those places, the region-based partitioning is very important. And does it mean that in those cases, we are going to do only region-based partitioning? We will do hybrid approach. We'll come to that later, where we do use multiple algorithms, not only one partition technique. We use multiple partition techniques, a combination for the better efficiency. For now, if you just see the disadvantage of this approach, this may not be sufficient enough to scale. For example, if you just see one bigger partition for entire US, the users base in the US is likely to be very high. So that partition is going to have lots of data. Compared to UK, the number of citizens here are quite lesser compared to US. Then UK partition is usually likely to have lesser data. So that's the reason the skews are more possible, and most of the time it may not be just sufficient because if one country is having huge amount of data. And the other option is, the other problem is complexity in the routing. So when a data center, when data partitioning is serving the request, we usually need to detect from which region, the load balancer is receiving a request, then it has to detect from which region is this request coming from. And then based on the location of the request, it has to send forward the request to the corresponding data center, the corresponding partition. Just looking at the IP address is may not be always possible, but because, for example, if you see in the enterprises, corporates, they do have a VPN and it's the same across the entire organization most of the times. So when it is working under the VPN within the organization, it may not be easy to just looking at the IP address to tell from which location this request is coming from. And unless the organization is maintaining a separate list of IPs for each of the locations, that's when they probably will be able to. I did one feature in the Cassandra related to this one. So, but it's very, very difficult to figure out from which location a request is coming from. That is another problem with the region-based partitioning. The fourth one we are coming is the functional partitioning. This functional partitioning is like a category of the data. For example, all users data in one partition, all orders data is another partition. If you assume Amazon account, our users data is in one partition, all orders in another partitioning. And this is very useful in case of the data the microservices, because usually there is one microservice working on the user data, another microservice working on the orders. Then it's more easy one-on-one mapping or simple mapping from the microservice to the actual category of the data. But the main problem with this approach is you really need to have so we really will have a very data skew, because if you see the number of users on Amazon account are going to be quite lesser compared to the number of orders. Orders going to be very, very huge. So it's very possible to have the data skew. That is one problem. Second problem, sorry, I didn't mention that here. Because we are doing partitioning based on the category, all users data going to one partition, then we will not be able to exploit the advantage of, I will just draw that advantage of the parallelism. So if the data is in different partitions, what we can do, there are something like map reduce kind of parallelism, where we can read the data parallelly from both the partitions in one shot and then merge the data here and send the data. So we try to access the data parallelly from multiple partitions. Whereas if the user's data is in one partition and orders data is another partition, then we will not be we will be reading from only single partition, and we will be blocked on the sequential read or the database reads on that one particular partition. So we will not be able to exploit the parallelism here. That is another problem with this approach.
Sorry, Shalja, can you just explain that again? I didn't follow how you were explaining the user data and the order data.
Okay, let's assume you're having users data here and the orders data here. Okay, now if I'm trying to read users the huge amount of data by any chance, if it's small query is not a problem, but if I'm trying to read huge amount of data from the users, this microservice, let's assume, is trying to read from the users database, then there will be, assuming all the users data is in couple of few partitions. When we are using users data for the partitioning scheme, let's assume there are few database reads. Orders data is in couple of many more partitions, let's assume. In this case, when you're trying to read from the users data, you will send a database reads to these ones and you will wait for the response. So if there are, in this case, we are limited by the throughput of these disks. So when you're doing the reads to disk, you are limited by how much efficiently this disk can give the throughput of the data when large amount of data is involved. Whereas if we are having many more partitions, what we can do, we can initiate all reads parallelly at the same time, the way MapReduce, for example, Spark does. You will say that, for example, orders from the January 1st to January 31st, we send the same request to all the partitions. We'll go and read data from this one. Let's assume this one is giving 100 records, this one giving 10, this one is giving 200 records, so on. Then what do? We do match this data. We take all this data, match them. Sometimes we may need to apply the filters as well based on the query. Match the data and return the data to the user, with the caller. So here, all these are working parallelly at the same time. So we are not limited by the disk throughput of any particular. I mean, we are not limited by the disk throughput of the one or two disks. So we are trying to say that, okay, asking 10 people, go and get the data, and I will do the match. Whereas in this case, we are limited by the fewer number of disks, and we need to keep reading lots of data from each of the disks. So that means we are having lesser parallelism. If the same data is spread to many more machines, then we would be having more parallelism. So that's the reason why the categorization using this data, using some particular type of the data is not so efficient. Did I answer your question?
I understood like how you said we spread the data more, so then we can incorporate parallel processing. What I didn't understand is like your this partitioning strategy. You're saying that it's used when there is you can partition by the type of data. Is that what the strategy was about?
Yeah, type of the data, the category of the data.
Okay, makes sense. Thank you.
It's not that we don't use it in real systems. We do use it. For example, we can say that this database is for this user table and this database for the orders table, but it has its own limitations unless, if not taking care about this parallelism properly, then it has its own limitations in the achieving the best throughput possible.
Yeah. Okay.
And the other problem is it involves joins. For example, if you want to get all the orders placed by a user using a subscription, then first you need to go to the users table, get what are the subscriptions made by this user, get the subscription numbers, then go to the orders table, get all the orders made by those subscriptions. So you need to read from one table first, get the data, and then go and read from another table and apply joins on them. This is how database usually work in the background. When you are applying the joins, read one data, filter them out, and read from another data, then try to do the map. And this requires joins. And joins are very costly in the database. Not only it requires a lot of data reading, then filtering, and then processing, applying merge on top of them. And because it requires reading lots of data, it creates a lot of memory pressure as well. So we try to reduce the joins wherever possible. So this method requires joins as well. This one, the functional partitioning. Is that clear?
Yeah.
And the other approach is the hash partitioning, and this is very frequently used one. It's most frequently used one, more efficient as well, but it has its own limitations. And that's the reason we will discuss about the better approach a bit later, about the improved hash partitioning. But right now, I'll just explain to you what is the hash partitioning. So in case of hash partitioning, what we do, for the incoming primary index or the partitioning index value, we apply hash algorithm. Sorry, my pencil is not good. We apply hash algorithm. It could be any hash algorithm. Right now, I'm not digging into what is exactly hash algorithm it is. I'm assuming that you already know what is a hash algorithm. There are many couple of popular ones. If you are interested in, you can dig into them. MD5, SHA-256, Murmur. So these are a bit more advanced hash algorithms. We do apply some hash algorithm on the column value or the set of column values, whatever is the primary index value. Take that value. Let's assume we are having 10 partitions. For simplicity, let's take them. We are having 4 partitions. Then whatever is the hash value, we can apply percentile n, or there are other ways of limiting as well. In this case, 4 partitions, we can say percentile 4. If you take a simple algorithm, let's say I take 1 percentile 4, the hash value is usually hash values are very bigger. We truncate the value and take very little tailing values or the head values. and then we apply the mod on top of that. Then 2 percentile 4, 3 percentile 4 is 3, 4 percentile 4 is 0. Let's assume we are having 0, 1, 2, 3 here. Now, if you go for 5 again, 5% 4 is again 1. It again goes 4. So 0, 1, 2, 3, 4, 5, 6, 7. So that's how data keeps distributing across multiple partitions. Now, in this case, you don't need to maintain any custom mapping. While writing the data, you applied a hash algorithm. You have written the data. And then while reading the data as well, you apply the same hash algorithm on the primary index and read the data back. That is how the simple hash partitioning works. The main problem with this approach, while it's very simple to implement and very efficient, because the hash is very faster to implement usually, though it says order of one, may not be exactly order of one based on the hash value calculations, but most of the processors support very efficient hash calculations in the hardware, so it's very efficient as well, calculation and inputting the data there. But the main problem is, let's assume there is one partitioning loss that machine is went down. Then this data need to be distributed. Not only that, when you're adding a new machine, the number of machines going up, let's assume 5. In the simple case, the resulting hash values also changes. So 0 percentile 5 is 0. 1, we get the same 1. 2, we get the same 2. 3, get the same 3. 4, we get the same. Again, when 5, we get the 0. So here 4 was going here before, but now 4 is going to the new node and 5 is coming here. So 5 is the data which was previously in this disk has to be moved here. 6 goes to 1. So this one will be moved here. This one will be moved here. So there is a lot of data to be moved. Whenever we add a new node, or whenever the data is, we have permanently took off a node from the system, the resulting hashing values changes for almost entire data. So almost entire data, there's a large portion of the data need to be redistributed into the other partitions. This is very costly operation because you need to read entire disk from here and go and write another place and read from entire place here, write another place. So it's like involves lot of disk reads and writes and across the network. So this is the reason the simple hash partitioning is not scalable as you add more and nodes and remove nodes. To avoid this problem, we have the consistent hashing. We will come to that later because that requires a bit more discussion. I have kept it at the end. So we'll come to the consistent hashing here.
I have one quick question. How does the hashing algorithm ensure that the data doesn't get skewed through the partitioning algorithm?
Yeah, so because here you are not when you are hashing the hashing the primary index value, the hashing algorithm usually needs to be such a way that there are not many synonyms. So if you 6 to SHA-256, it's very efficient. The possibility of collisions is very, very low. That means two different data falling to the same partitioning is usually very, very low. So that means if you're given a range of the data 1 to n, and it's likely that all those 1 to n are getting the different hash values, and then when you apply the mod operations or truncate them to a set of nodes, like 10 nodes, it's very high likely that that data is falling to within a equally falling to within the set of machines. It need not be exactly equal. For example, there can be mild variation. For example, in the 100 data values, probably this one is getting so high 100, this one is getting 25 records, this one is getting 20 records, this can get 30. So there can be little mild variation, but doesn't create as much skew as we discussed with the other approaches, because the hash algorithm is it's nothing to do with what type of data it is. It's nothing to do with the region or the functionality category of the data. It's a simple, very value of doing some application, rolling the value, applying, multiplying the value. For example, simple hash value can be, you take a primary index value and you apply a hash calculation on top of that, come up with a 64-bit value. On top of that, you can probably do multiplication by some odd numbers. So if you use the hash algorithms, they do use very particular, very big odd values to create that, reduce the possibility of creating the synonyms. So, and then they do roll the value, and again they have apply multiply with some other odd value. So if you see these algorithms, they look very simple, but how they create the different hash values to avoid the synonyms is really magic, very awesome. So if we have time at the end, we can go through a couple of the hash algorithms, but usually these are simple. These are really efficient. We need to sit and debug how it's going on, but it's not really lots of code. Probably if I check some calculation, the hash calculation doesn't have more than 10 to 20 lines of the code. But it's in the logic, the way they do use those particular numbers, they do rotate the numbers. That's where it's important.
Okay, so you're saying that there will be enough randomness that will ensure
Exactly.
Good enough even distribution.
They use those particular values to introduce the randomness. Actual data may not be having the randomness, but they introduce those numbers. So even if there's one bit difference from one primary index value to another primary index value, the hash value generated will be very different.
Right.
But there is still possibility, right, to have a hotspot. I mean, for example, if we have celebrities and we have we're having a hashing strategy, which is you just discussed. But for example, if celebrities is living on this shard, so it will be skew data, right? In this case, we can't prevent it with consist hashing.
Okay. So the one you're discussing is users data. So, for example, if a particular celebrity uses a profile data, if that profile data, so actually we are a bit mixing this with the functional partitioning. For example, if you simply take a Facebook page, let's assume very popular person, just our favorite, let's assume Trump.
And book profile, for example, if you take from user from Amazon and he has a lot of orders, so for example, also it will be like hotspot because we need to fetch all the orders because we make partition based on ID of user ID, for example.
So that's exactly in the case of orders, the primary index we choose equally responsible. In case of orders, the primary index we choose is the partition index we choose is the order ID. Order ID is nothing to do with the user ID. So order ID itself is not. So when you're using order ID, that is a efficient primary index.
I'm using, for example, user ID with a lot of order.
Yeah, so that's the reason when user is also equally responsible to you will choose the right partition index. If they choose a wrong partition index, there is nothing our partitioning scheme is going to stop them. For example, if I just use in order IDs, if I just use a simple location as a partitioning index, then all the orders particular belonging to yes will go to the same same partition. So that is nothing we can stop when in the backend where we as a storage systems or the replication systems, we cannot stop. When we are designing the system, when we are creating the table schema, the data modeling, we need to choose the partitioning index such a way that it is not going to create the skews. So that's the reason. If we even if we are going with the hash partitioning, if the primary partitioning index chosen is not the right one, is not correct data modeling, that's when the skews happen. So what we usually do as a database provider, as a storage system provider, when customers comes to us saying that they have latency problems or they are having data skews or their queries are timing out, we go look at their schema, we try to understand their access patterns, then we recommend them how to remodel the table, the database. That's the reason there are jobs for the database the modeling. I mean, what we call them, database analysts or something. So there is a reason they are specialized in that database modeling.
But what if, like what Lilia is saying is, let's say my partition index is the one that's heavily used in my query. Let's say, for example, user ID is the one I heavily use in my query. But I also can't guarantee that this will be, there will be a variety of it, as in there'll be a lot of common data, which will then risk us having a not skewed data, right? Like that even distribution problem will come back. So how do we ensure that, do you suggest that then we should mix it with another random, with another partition index that will create the randomness?
There are a couple of strategies for this one. One of them is, as you mentioned, instead of just using one column, which can have a lot of duplication, we use a couple of combination of the columns. It could be user ID and order ID combination or something. That way, that's how, even in that case, even if you're having user ID and order ID combination, you can still have efficient reads based on the user ID, because it is a prefix that I did list that in the comp later on for the discussion, but I will just quickly show it to you. So one approach is, let's assume in the primary index you're having two columns. Simple, it's not an ideal strategy, but I'm just using to so that you can understand for this particular situation. Let's say user ID and order ID. And you were while distributing the data, while writing, you're using these two columns together to distribute the data into multiple systems. Sorry, my diagram is not good. But when you're reading, you probably, even if you're providing just the user ID, let's assume you're giving the user ID. For the order ID, we don't need to filter based on the order ID. We go and get the data from the corresponding portion. This may involve not going to exactly the correct portion and going and getting the data, but still this is slightly better compared to not having from reading from a column which doesn't have any index on that. So can I put an example? So let's assume if when you simple range portion you can take, you're saying that you're having user ID 1 and order ID 1 here, user ID 1, order ID 2 here, and then you're having user ID 1, 3 here, user ID and 4, so on, and 1, 5, 1, 6. So when you're reading based on the both user ID order ID, let's assume you're reading based on 1, 4, you will immediately go to the directly to the which portion the data is there and read from there. Whereas if the read is based on only 1, the 4 is not provided, you will go to the all the portions which is having the 1. You read all this data and then you will do the merge of the data. So that is something like map reducer spark parallelism, where we go to the multiple portions, read them parallelly, and you merge the data. So it's not as efficient as is directly providing entire portion index here, but still better than not having for some column which is not part of the partitioning index at all. This column, we don't know on which portions this belongs to. We have to go through all the instances of the database. We need to read entire sequential scan of every table, then filter out the data and get it back. In those cases, what we use, the other option is a secondary index. So second, instead of going for the, if the data we are accessing more frequently on a particular column, which is not part of the partitioning index, then we create a secondary index on them. A secondary index, it maintains another index. For example, it says that if I'm trying to access based on, let's assume my partitioning is only an order ID, not on the user ID. But I'm trying to read based on the user ID quite frequently. Then what we do, there is another table. It's a hidden table. You won't see that, but the database do have a hidden table. It maintains says that user ID U is having these many orders, 1, 2, 3, 4, 5, 6. It doesn't maintain actual original data there. It maintains pointers to those corresponding records. You can say as a row IDs. So this one is a row ID R1, R2, R3, so on. Then it maintains those pointers. Now, when you're reading based on the secondary index, it first goes to this hidden table, takes the secondary index value, takes the corresponding primary actual index values row IDs, goes to all these partitions, reads them directly because we are already having the row ID, the pointers to the actual database values, then we go and read them directly. So second index is very useful in that case to read based on a column which is not part of the partitioning index, but there is a penalty involved with the secondary index. In case of secondary indexes, what happens? Because we are maintaining mapping in another hidden table here, let's assume there is a change to the user ID, UID, the order ID value. Let's assume order ID 5 is having a change. Let's say 7, 5 is dropped out and 7 is added. Let's assume then when the actual data in the actual partition changes, whenever there is actual original data changed, the database has to go and update the secondary index as well. That means we are trying to do one row write, one row update. For you, it's a one row update. For the database, it's a 2 rows update. One, the actual update. Second, the hidden secondary index table update. And the more secondary index you have, you can have as many secondary indexes as you want. The more secondary indexes you have, the more writes it has to do during the actual write operation. That means a simple write operation latency will go up. So that's the reason there are multiple, when you are data modeling a table, you try to distribute the data and also tries to use the frequently used column as part of the partitioning index. If that's not sufficient for any situations, then we try to have secondary indexes on the frequently used columns, which are not part of the primary partitioning index, but still we need to try to reduce the skews because partitioning index is the place which is the important one to distribute the data. So partitioning index still need to try to distribute the data across multiple partitions. But the secondary index doesn't have to worry about that. Secondary index just need to worry about using the frequently used column for accessing the data.
Okay, that makes sense. Sorry, I don't want to start a new topic, but just one quick clarification. The secondary index is what we call reverse index or elastic. This is what
no, those are different ones. So I will explain them. We are coming to them soon. So here we are mentioning them here. We will come to them sooner.
Okay, sorry. Thank you.
Okay, now coming to the now we are just done with the hash partitioning. Yeah, so this is very important when the hash partitioning that I shouldn't miss. The range query is going to be very inefficient with the hash partitioning. So the main reason, because we are distributing the data based on hash value, which doesn't take care of the what is the incoming actual value or partition index. The data can be just randomly going to different partitions. When you want to do the range partitioning, for example, if I want to read, if I want to read all the users, let's assume with the name WCC, starting with WCC or something, then this same WCC and another index, for example, let's assume all the users in the WCC going to the system design class. Let's assume if these two are the part of the primary index, then not exactly. So I need to really frame a proper one. Let's assume I need to find out users with simply let's assume from the age from 1 to 10. Okay, sorry, it's 20 to 30. I'm really not children here. So let's assume 20 to 30. We need to find out. Then if we are if the partitioning is on this value, these values can go to very different partitions. When we want to do the range queries, it is not possible to co-locate one disk. These are all not located on the same disk consecutively. It could be going into different partitions and randomly places at different places. So in this case, you need to go to all the disks and issue the reads and then do the merge. Whereas in case of the range partitioning, the main advantage is once you look at the first one, all the records with the values consecutive to each other. So WCC age 20, WCC the age 21, so on. They're all they all sit adjacent to each other. So once in the B-tree index, in the B-tree, once you look at the first record, you will just go and issue the sequential reader with all the records in the range partitioning. This is not possible with the hash partitioning, because hash partitioning this sends these records to different systems. So you need to issue reads to all the partitionings in one shot, read them, merge them together. So it involves the whenever there is a all partitions read and we try to merge them together, we need to put all the records in memory, and then we need to merge them. That requires the triggers a merge pressure, and merge is a kind of bottleneck, because there should be one coordinator sitting and doing the merge operation there. So the range queries are not going to be efficient at all with the hash partitioning. This is very important. These two things you need to remember very clearly for system design interview. If your use case requires range queries, better you go for the range partitioning, but not hash partitioning, because hash partitioning doesn't support the range well. Other way around, if your system doesn't require range partitioning, then you don't need to go for it doesn't your system design doesn't have a range queries use case, then you can most likely go for the hash partitioning. Hash partitioning doesn't support the range queries well, but it's efficient in distributing the data, avoiding the skews. So these 2 points you need to remember very carefully. Is that clear?
Did you say hash partitioning doesn't support range?
Exactly. Yes, range queries, because if you see, if you just forget about the partitioning altogether, just to look into the data structures wise. If you see, just take a simple, you forget about the B tree as well, simple binary search tree. Okay, simple binary search tree. What you do in a binary search tree, you write key value pairs. Once in the binary search tree, we can do range queries, because once we locate a key, all the consecutive values are going to be within the adjacent nodes. So we find one key, then you keep reading of all consecutive nodes as long as the criteria matches. For example, this is your B tree is going to be more efficient, but simply let's assume your binary search tree. Okay. So on. So in the binary search tree, the key value pairs are written here. Once you locate a key, all consecutive values can be read. And this is going to be more efficient with the B tree, because B trees, these blocks are very huge. How are they going to be located? This is the B tree. It contains indexes of various blocks. This one going to have more indexes. If you take one simple block, it is going to have all the values consecutive. Let's say 1, 2, 3, 4, 5, 6. Let's assume these are age values. Simply, let's assume. Once you locate one record, this disk block is already in memory. Even to read even 1 bit value from the disk block, it has to be read into memory first. So this block read into in-memory RAM here. You kept the values here, so on. Then you read one. Then if it is a range query, you come, let's assume I'm trying to get all the values from 1 to 10. You keep reading until 11 comes. When the moment 11 comes, we stop that, because the B tree value keys are sorted. We know that after 11, there is no data going to be falling into the my criteria. So we just read this 10, and this is going to be a sequential read in the disk blocks, which is already in memory. So the range query is going to be very efficient in case of tree lookups. So, whereas in case of one, hash indexes, this is your hash table. Let's take the same values 1, 2, 2, and so on 20. 1 probably is here, 2 is here, because we do introduce this anonymousness there, and the values can be somewhere randomly anywhere, 3, so on. When you try to read the range queries, you need to read one from, you need to take the one, hash it, go and read from here, 2, hash it, read from here, 3, go and hash it, read from here. So you're not taking advantage of this. Probably are located in the different disk blocks. Let's assume this one is in disk block D1, this one is D5, this one is, let's say, disk 20. You need to read this one into the RAM, this disk block into RAM, this disk block into the RAM, this block into RAM. So this reads involves multiple disk blocks into the RAM, and you can't really just having one disk block, a couple of disk blocks, you can't really exploit the uh, range option, because these are not consecutively located. Hash is not hash is made it so anonymous that they are not consecutively located to adjacently located to each other. So range anything related to range is not good with hash mechanism. So it need not be just the data distribution. Even if you are doing the lead code programming, we need to, when the problem is given, if the problem involves anything related to range, then better not use a hash. Go for the tree. It could be binary search tree, or it could be speed tree, or anything, or whatever your choice in the coding program problem. If it is a range a requirement, go to the tree. Otherwise, go to the hash. If it is the access that doesn't require range, but in that case, you can exploit the hash because it's order of one operation most of the times. Is that clear?
Yeah.
Okay. Now we come to the hybrid partitioning. The hybrid partitioning is a, as I mentioned, is a combination of multiple partitioning techniques. It could be, as we mentioned before, if we are going for geo-based partitioning, US data within the US, UK data within the UK. Even then, the geo-based partitioning just alone is not sufficient. Within the US, you can probably having different partitioning. So, for example, geo plus hash, or it could be geo plus geo as well. For example, within the US, then by city, you're going by country and then by city. That way, you're putting all the city level values in one partition and all the US level values in the partition. And then it could be geo plus range. Then you can be using the tree and going for a range. So that means if I say all the users located in US with the name starting with Michael, then I can go to the just directly go to the US partition. Then I can start range querying the tree based on the name starting with Michael. So you can utilize multiple combination of multiple strategies together. There is no limit on which combinations works well. Whatever based on your use case, you can go for anyone whichever works best for that. So it's not like a where you just read somewhere and you know that okay, this is going to work. You need to keep practicing. The more and more practicing, you'll be able to identify what is the best mechanism, what is the one which is going to create data skews, how is it going to impact the read, how is it going to impact the write, so on. So we will be looking at various examples when we do the mock system design, once we are done with the basic concepts in the upcoming few sessions. And during every system design, the data partitioning technique could be different from the different system based on the use case. Now coming to the consistency hashing. So this is very important, consistency hashing. Probably you may need to use it or not use it in the system design interview based on the complexity and given problem. But it's very important to understand, because in most of the nowadays systems like leaderless systems like Cassandra, DynamoDB, or many even Spanner, I guess, most of the practical systems use consistent hashing. And there are many different techniques as well, but this is very, very popular because it's practically used at all many places. So better you understand it correctly. Okay, let me explain this. In case if you have any questions in the consistent hashing, ask me now because it's a very important concept. Now, I will just quickly show you how it's going to work. Let me just use it to this one. Let me make space here. Delete option. Oh no. Let me go other side then. Yeah. Okay. Yeah. So in case of the consistency hashing, what we do, we assume the usually typical hash table. Why how we assume it's like a this one, table. Instead of table format, let's assume it is 1 to 2 so on. For simplicity, let's take on. We're having numbers like 32 maybe. I want to have smaller numbers so we can show it the same one here. We just assume this one like a ring. So we assume 0, 1, 2, 3, so on, 4, 5, 6, 7, so on, 32 here. Let's make some numbers 6, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so on. So it's 32. So just physically it's not going to be like that. Just assume they are attached. You're having a ring now. Okay. Now you place the nodes, the machines that we were thinking, we were assuming before. Those you just assume those are here. Let's assume I have 4 nodes for now. I'll just take 4 nodes. One node here. I can place them anywhere. It's actually the most of the practical algorithms are randomly chosen tokens that randomly we choose. But at the same time, you can manually choose where you want to put in the real system, even in Cassandra, or you can have a small algorithm to randomly choose ensuring the uniform distribution, but there is no particular algorithm for the placing the nodes there. Okay, so let's assume node N1, node N2, node N3, node N4. So you are just assigning these numbers here. Node N1 is here at 0. Let's assume node N1 is 32, is somewhere around, my numbering is not correct, it's around 8, 16, 32. Okay, these are the token assigned to the nodes. Now, the nodes are assumed in some places on the hash ring. Whenever incoming requests come, let's assume the primary index value, you hash the same way as you do in the hash partitioning strategy. The same way, you take the partition index value, you apply some hash value, and then do the percentile by the total ring size. So let's assume that whatever 32 in the ring size, you take that incoming value. Let's assume it was 0. It comes the incoming partitioning index value comes here to here. We call it key. The value we get after applying the hash value we get after applying hash algorithm and the modulo everything, we just call it this value as a key for simplicity here. So if it is 0 or 1 so on, from 0 to 8, let's assume here I don't have space here to write 1, 2, 3 so on up to 8. All these requests with the keys from 0 to 8, keys means here on the partition index after applying the hash value and the whatever the hash algorithm and modulo everything, the resulting value. If those are falling in this range, those requests go to the node N2. Those gets written to N2, gets read from the N2. Okay, and all the values from this 8 to 16, which are falling here, goes to N3. And this one goes to N4. this one goes for this one. Okay, there is nothing asking you to go only to this node. You can do the reverse logic as well, but for some reason there is a universal acceptance that we go clockwise, and there's nothing specific reason for that. There is a people just agreed on that rule, I guess. Okay, so in the whatever the range falling from this node to the node below that, that goes to this node, the clockwise. So the one advantage of this approach is it ensures that distribution of the value keys, distribution of the incoming values to the nodes equally, or need not be exactly equally, but reducing the skew proportionally, you can say. Assume that logically this range is going to one node, this range is going to another node, so on, but we are depicting the same one in the circular fashion. In the physical way, there is nothing else putting you in the ring fashion. There is no ring physically there. There is nothing there. It's all in the logic, just the logic. Okay, so you're all putting on in the hash table the range into different nodes. Now, while this works fine, this is a simpler consistent hashing. The main problem is, let's assume node 2 died. Okay, node 2 died. In that case, all the data, which is this one, which was going to N2 before, now has to go to N3. Don't worry, this whenever node 2 has died, we retrieve this data from the replicas. There is we use a consistent hashing algorithm for replicas as well. I will cover that later, but right now I want to make it as simple as possible. Okay, now all the data which was going to N2 now has to be migrated, physically migrated, because this 2 was on the node 2, which died, which is no longer accessible. That means this data which we recover from the replicas or from the write headlock, whatever the we recovered, we then go and write them into the entity. That means physically move the data. This requires physical movement and redistribution. That is the one thing, redistribution of the data. The other problem is now N3 is going to have higher value. Previously, every node was getting 8 values. Now this one is getting 16 values. So in this small number, it don't look like a really big value for N3, but in real bigger numbers, when there are 2 power 64 number of possible values or data, different values possible, it can be really huge, can be a lot of data for one node to take. So in the improved consistency hashing, we try to reduce this possibility by introducing multiple instances of the same node in multiple places on the ring. We call them as a virtual nodes. Let's assume this is one node. We divide them into 4 parts, let's assume, or simply 3 parts to make it simpler for the diagram. It doesn't mean we are going to really go split this disk into this machine into 3 parts. No, just logically assume that. You can even simply assume that in your disk, we are creating 3 disk partitions or 3 directories, simply D1, D2, D3. So for each of the multiple instances, simply that's if that makes it easy to understand D1, D2, D3, so on. For each of them, D1, D2, D3, 3 folders, let's assume. Okay. Now, what we do for each of the machine N1, yeah, okay, for the N1 we create N1 D1, let's assume the a virtual node. You can say this folder D1 as a node for a while within the same machine. Then you probably put another N1 D2 here, N1 D3 here. That means the same machine but multiple virtual partitions. So we call them V nodes, virtual nodes. Okay. For the system, it's just another node. Doesn't matter to it. Is it in the same machine or different machine? Just another node. Now for the same N2, you do the same one. I'm just using different colors so you can. So let's assume we randomly choose them to avoid the skewing. If you're not properly chosen, this can also create a skew. So we need to ensure it's properly doing. And let's assume somewhere.
Yes, I'm very sorry
Enter.
to interrupt. Just to want to tell you that we are running a lot of out of time.
Oh no, I didn't know that we were going to take
No
so
worries.
much
Thank
time.
you so much for. I believe the session is quite cool. People is all people are staying actually because today you are very detailed, and you're answering questions. So it's
Actually, if we can have 10 minutes, if everyone is
yeah,
okay, I would like
yeah,
to finish this
definitely.
consistent sashing. The remaining, I can again try to cover in the next session, but I would like to finish this one because
Yes.
the first one we covered is going to very correlated to the second one. I don't want your memory to be flushed out. Uh, is that okay for everyone?
To have 10 more minutes.
Yeah, just 10. Maybe 10, not even 10, 5 minutes should be sufficient.
Yeah, cool.
Okay.
Thank you.
Then we are having a, let's say, N3, N3 D1 and N3 D2 and N3 D3, let's assume. So now this logic is the same again. All the values come falling in between this, going to this node, so on. But what we are doing is we are trying to create a smaller range. So if N2 dies, for example, in this case, N2 dies, this means if the entire node is dead, this all the instances also gone. The amount of data to be redistributed is going to be smaller. This data going to be this one. This data going to be this one. Sorry, again, I did the wrong. I created this queue here. Ideally, the green one died. So if you see, I created a skew. All the data of the diode node is taken by the blue one only. But ideally, we need to choose the node location such a way that the new data is equally spread across all the available nodes. So both red and blue should be equally taking them. So I should probably just swapping these two will take it, will avoid the skew wherever possible. So we try to reduce the skew by creating multiple virtual nodes of the same node and putting them in randomly across the ring, ensuring the uniform distribution. So if one node dies, the resulting data should be taken by other nodes or almost equally. So I will create a better diagram of this next time so that I can show you how to avoid this queuing when a one node dies. Similarly, when we add a new node as well, we try to reduce the skew wherever possible. But I will repeat this consistency hashing, the advanced one, because it's very important one in the next coming session. Yeah, so any questions? Sorry, I couldn't take the questions in between because I will forget what I was speaking otherwise.
I have one quick question here, Sharja. I didn't understand what is the I mean, if you said we are creating a virtual node of all the remaining nodes, right? How is that different from adding the data to the same node? Like, what is the I didn't understand what a virtual node here.
For the nodes, from the node perspective, it doesn't care what is the data it is getting. From the distribution perspective, that's the reason I wanted to create a better diagram here. So now, in this case, all these are blue. Let's assume this one is 2. 2 is the one which died, right? So we'll N3, N1. Let's assume this one is N1. This one is N3. And this one is N3. I should ideally have another one. So assuming this one is having 4 keys, and this one is this one here is 4 keys, then this one is again 4 keys. Let's assume, yeah, here to here. When the green one died, these 4 keys moved to the N1. N1 got plus 4, extra 4. And then this one, so N3 got plus 4. Then again this one, N3 got plus 4. So my diagram really didn't avoid the skew, but real systems place the server such a way that to avoid the skew. So if the died node is having, let's assume 10 keys, and the remaining alive nodes are let's assume 5 nodes, then each node try to take equal proportion of the died node, like 2, 2, 2, 2. So it's something like uh, one person in our team left the team. Then instead of another person taking all his work, we all remaining team members, let's say 4 members, we take equal proportion of the work, so it doesn't create load to one single person. I will come up with the proper diagram next time, so I can show you how it equally distributes the data with the alive nodes. Okay.
Is this for, so the distribution of the data, well, in between the alive nodes, that's for the data that was already retained on the dead node, right? But for the new data that is getting now streamed into this system, it will calculate the hashing based on the present 3 nodes, isn't it? It's not based on the present, the past 4 nodes, but it's now based on the 3 nodes that are present in the current.
So the hashing of the value in this case doesn't look for the number of nodes. It just looks the range. So the hashing, the modulo we did in the hash partitioning, you based on the number of available nodes. We don't do that here. So for example, if the range value is 0 to 64, 0 to 32 in our example before, so 0 all the way to 32, 0, 1, so on. Even when the node dies or a new node added, this range remains the same. So that's the same. Only the nodes which are placed, which died, and new nodes added somewhere. So that's the reason the range of the data values doesn't change in this case. Whereas the hash partitioning case, because we were doing the modulo by number of nodes, it was changing. We don't change that here.
So there is. So are you saying there is hashing here, like the algorithm, like a SHA-256 is applied, but we then don't incorporate the number of nodes in any formula to.
Exactly. So because the number of nodes, we wanted them to be vary. As we add nodes, we want to remove nodes. We want to let the number of nodes to be varying. That's the reason we don't do the modulo number of nodes in this case. Instead of that, we place nodes randomly across the hash table, and then we move the data based on the particular logic of locating a next node clockwise. So just ignore this diagram because I didn't create a proper example here. I will show you with proper example. Next session, we will again repeat the consistency hashing with this advanced example better because it's very important concept. But we usually don't take the number of nodes in the hash value of the incoming value, primary index, the partitioning index.
No worries. I will wait for the next session. Thank you.
Yeah, sorry, I couldn't take your questions before, so let me quickly go through the questions. Can we see partitioning splitting the data? Say partitioning and sharding are the both. It's the same scheme, same thing, but different wording. So partitioning, sharding is the same. Shard, it means a piece of the data. Partitioning is creating a piece of the data, is the same. So just assume both are exactly the same. Don't need to worry about that. In the same machine, which sharding is splitting the data into more. Partitioning and sharding, depending on the strategy used for creating the partition shard, it can be within the same machine, it can be across the machines. So it's nothing to do with the partitioning and sharding is the same. Or partitioning on different databases. So partitioning, the one we are discussing, it is a very generic logic. We are discussing strategies. It can be used for the data partitioning on different databases or data partitioning within the database based on if it is a distributed database. The distributed database itself probably doing internally partitioning and sharding, or it can be used by the load balancer for distributing the incoming requests across. So it's overall the one we are discussing is a strategy to distribute. It can be data, it can be incoming requests, a strategy to distribute the incoming things across multiple machines in the system. Can we say partitioning is splitting the data in the same machine? Well, no, this is, I did answer. No, this is not true. Partitioning and sharding is the same, and it can be within the machine, it can be across the machines. How
no,
you are doing.
let's not go deep here. I can post it on the Slack. Nada is right. there is some it's existing concept that partitioning. It's what she posted. It is true. I will post it article if you want on this.
Okay.
Yeah.
Then,
You can just go to answer this question, and we can communicate it on the Slack. Just don't want to take time because we are very beyond of the time,
Yeah.
and I have in 15 minutes another meeting.
Yeah, I can't really read so fast. Next session, first 10 minutes, we'll take the questions then.
Yeah, thank you so much.
And I can ask a quick question, please. You mentioned to get used to all the different strategies, it's good just to practice, and the more you practice. But if it's not in your job, then you mentioned use cases that you'll be covering later on. Is there anywhere else? Do you have any other resources where we can look for lots of use cases where we can see the different strategies being used to become
The more and more you do mock system designs, you read about them or you do on your own, you'll be able to understand what is going wrong with each of the strategies. We can read about them, as I mentioned, I explained them, but the theory is very different from the practicals. When we are really doing the practicals, that's when you realize what's really going wrong with each of the different use cases. So you read them, but still, you try to do the mock system designs and try to think through what is the strategy I want to use for this particular use case, and then you will realize what is the problem with each of the approach. So even in this real system design, if you're using the wrong approach, it's okay, as long as you're able to justify why it's not so good one for the use case, and then you come up with the good one for use case, then that's fine.
Okay, thank you.
Yeah, so we will do that more mock system designs when we are done with the concepts. That's when you will see the actual practicals.
Yes, this was a very nice session. Thank you so much.
Thank you. Bye.
Yeah, and we will take all the questions next session. So yeah, thank you so much, folks. And very sorry that we ran it. Okay, I'm
Thank you all.
call. Yeah, Nada, go ahead. You have question or what?
No, I just say thank you.
Okay, cool.
Bye.
Bye, folks. I will stop recording now.